Welcome back to the deep dive. Okay, today we're looking at a research paper that, honestly, it pulled off a great bit of misdirection.
hmm
The title is simply DeepSeek OCR, optical character recognition. So you see that and think, okay, fine, another small step in getting text off a page.
Exactly. Sounds very, very incremental.
Yeah.
But when you actually get into it, what the paper's really proposing is, well, it's a pretty fundamental shift in architecture.
Right.
They're not just tweaking character recognition, they're tackling the whole context problem for large language models. It's really about optical context compression.
Which is something we desperately need. We've seen LLMs just choke on huge inputs. Think of massive manuals, long contracts, years of reports.
Yeah, because the context window gets too big and the cost, that n squared attention cost, it just skyrockets.
So the DeepSeek team comes along and says, essentially, look, treat the image of the text as the compact carrier of information. And they claim this gets them close to a 10x effective compression ratio.
Which is kind of wild. And what's really interesting is how it's compressed. It's optimized specifically for the LLM's attention mechanism.
Okay.
So you bypass that whole problem of blowing up the token count with transcribed text. It offers a cheaper, probably faster way for models to reason
Right.
over, entire documents, not just snippets pulled by RAG.
Right. RAG is great for finding things, but not always for understanding the whole picture.
Exactly.
So for you listening, our mission today is to unpack this 10x claim. How does this compressed vision thing actually work? What does it mean for the cost of running LLMs? And, is the future context window maybe not bigger, but just smarter?
Let's dive in.
Okay, let's start with the old way, the traditional process. It seems, well, pretty clumsy now looking back. When a standard vision language model sees text in an image, what's the usual expensive road it takes?
Oh, it's super inefficient. Basically, the model have to first detect all the characters on the page, like visually identify them. Then it transcribes that visual info into just a long string of text. And that text string is what gets tokenized and fed into the language model part.
And that's where the bloat happens.
That's exactly it. A single dense page. Easily 800, maybe 1,000, even more, discrete text tokens. And when you start stacking pages, that token inflation just kills your budget and your speed.
Okay, but DeepSeek flips that script completely,
Right.
right? They don't rush to transcribe.
Precisely. They compress the visual input first. The document image itself gets squeezed down into a really small set of highly dense vision tokens. These are latent vectors, basically.
Right.
And then the decoder, the language model part, it just learns to read the text directly from these compact visual codes. Skips the middleman, the text transcription step.
It sounds almost too good to be true. But they have numbers, a core stat.
They do. They point to benchmarks like the Fox data set, which has these really dense pages, often over 1,000 actual text tokens.
Oh.
And the DeepSeek system gets around 97% decoding accuracy using maybe only a tenth of that number in vision tokens. So 100 vision tokens instead of 1,000 text tokens, roughly.
Wow. 97% accuracy with a 10-to-1 reduction. That's
Then
significant.
That's the key number. It shows this isn't just theoretical, it's computationally useful. The insight is the model attends to, say, 100 visual tokens, the kind of visual gist, not the 1,000 individual text characters. But it still reconstructs the full content.
So the compression isn't about saving disk space. It's about saving GPU cycles in the attention layers.
Exactly. That's the breakthrough. It's computational compression.
Okay, if that 10x really holds up, this could fundamentally change the economics of document AI. Let's get into those advantages. What does this 10x compression actually deliver?
Well, the first and maybe the most obvious one is it makes really large context windows actually tractable, practical.
Right.
If you could represent, say, 1,000 words with just 100-ish vision tokens, suddenly processing a multi-hundred-page document doesn't seem like this insane cost sink anymore. It becomes feasible.
It's a direct assault on that quadratic scaling problem for attention.
It is. And the second idea, I find this one really, really clever because it feels so human. It's a potential path towards useful memory decay.
Memory decay, like how our own memories work.
Yeah, kind of. Think about it. Older memories, they tend to fade, right? The sharp details blur, but you often keep the gist, the main structure. So they suggest you could take older context, like the beginning of a very long chat or the early chapters of a book. The model is render that text into an image, and then over time, you could progressively shrink the resolution of that image.
Huh. Okay, but wait. Let me push back a bit here. If you're shrinking the resolution, you're losing information, right? Intentionally. Doesn't that risk the model just making things up later if it needs a specific detail from that blurry part?
That's a totally fair question. Yes, you are introducing controlled information loss,
Yeah.
but look at the trade-off. You get potentially huge gains in capacity for just general understanding. Following the thread of a long document, that low-res image, which needs way fewer tokens, is often perfectly fine. It keeps the gist available.
Right.
And if the model realizes, hang on, I really need that exact number from chapter 2, well, maybe it flags that memory chunk as needing higher fidelity, or it triggers a traditional RAG lookup for the original text. But for just maintaining overall context, it frees up massive amounts of compute.
Okay, that makes sense. It's like an intelligent triage for memory. Keep the important stuff sharp, let the rest fade gracefully, but stay accessible.
Precisely. And that leads right into the third point, actual production savings.
Lower costs.
Exactly. Lower inference cost and less VRAM needed. Fewer tokens flowing through those dense attention layers means the initial processing, the prefill, is faster. And the memory required to hold the context is smaller.
So the upfront cost of encoding the image pays off on every single attention calculation after that.
That's the idea. And the scale they're talking about isn't trivial. They mention being able to generate training data, which uses this process at 200,000 pages per day on just one A100 GPU.
Wow.
Scale that up slightly, say 20 nodes, and you're talking tens of millions of pages a day. It turns massive document processing from this, supercomputer level problem into something much more manageable, almost routine.
That really does change the game for how quickly you can process document archives or build data sets. Okay, so how did they actually build this thing? Let's peek under the hood a bit. The deep encoder architecture, that's the compression engine, right?
Right. The whole system has two main parts. There's the deep encoder, which does the heavy lifting of compression, and then a pretty compact decoder that actually reads the compressed visual tokens and spits out the text.
And the decoder is optimized too.
Yeah, it's a 3 billion parameter mixture of experts, model, and a MOE, which sounds huge, but the trick with MOE is that for any given token, only a small fraction of the model is actually active. Here, it's about 570 million parameters per token. So it's computationally quite lean for its size.
Okay, so the reading part is efficient, but the magic happens in the deep encoder. How does it squeeze a whole page into, 100 tokens?
It's basically a two-stage process, kind of mimicking how we might scan a page. Stage 1 is about local perception, zooming in on the details, like reading a specific paragraph. They mention a SAM-style approach here.
Segment anything model, right. Good for fine details.
Exactly. Then Stage 2 handles global context. This is like glancing at the whole page, seeing the layout, where the headings are, if there's a big chart. More like a C-LIPE-style understanding.
Okay, local and global views. How are they connected?
Through a pretty aggressive convolutional compressor. It sits between these stages and basically takes the raw visual information, which might start as thousands of little image patches, and radically cuts down that number before the main global attention mechanism even sees it. They mentioned going from 4,096 patch tokens down to maybe 256.
Ah, so it compresses the raw visual data before the expensive attention part. That's clever.
That's the core mechanism. And crucially, they didn't just build one size fits all. They give you options, these flexible modes, like knobs you can turn.
To trade off cost and quality depending on the document?
Exactly. There's a tiny mode, just 64 tokens, probably best for simple stuff like presentation slides.
Okay.
Then there's small mode at 100 tokens. They position this as the strong default for most regular documents, PDFs, reports, that kind of thing. Seems like a workhorse.
Makes sense.
Then you can ramp it up. Base mode is 256 tokens, large is 400. You'd use these for denser stuff, maybe complex academic papers, things with lots of formulas or footnotes.
And then there's the ultimate mode, Gundam.
Yeah, Gundam mode, love the name. It uses around 795 tokens. That's for the really tough cases.
Like what, crazy spreadsheets? Old newspapers?
Exactly. Think dense financial tables spilling across pages, giant scientific posters with tons of tiny text and figures, really complex newspaper layouts. It handles that by using multiple tiled local views plus the overall global view.
So it's expensive for this system. It's still way, way cheaper than trying to process the thousands and thousands of text tokens you'd get from transcribing that kind of page normally.
Precisely. Still a massive saving compared to the traditional approach. And another key point, the output isn't just raw text dumped out.
Oh.
You can guide it with prompts. Like you can ask for clean layout-aware Markdown output.
Mm-hmm.
It will try to preserve section structure, keep tables formatted as tables, identify headings.
So it's not just reading, it's actually structuring the information as it extracts it. That's valuable downstream.
Hugely valuable, saves a ton of post-processing work.
Okay, so the performance sounds like it goes beyond just getting the words right. What other kinds of deep parsing can it do?
Yeah, it's pretty impressive. The paper shows examples of it taking like bar charts or graphs from a document and directly outputting a structured data table representing that chart.
Wow, okay.
It could look at chemical diagrams and output the corresponding smile string. That's the standard text format for molecules. It could even apparently recover geometric figures. So it's doing a form of understanding, not just transcription. It's creating structured data from visuals.
And it's multilingual too, trained on data from many languages.
Yeah, they mentioned training on large PDF corpora covering nearly 100 languages, so it should have pretty broad applicability.
But we should be realistic. What are the limitations? Where does it still struggle?
Well, like most OCR, really messy or inconsistent handwriting is still probably very tough. That remains a hard problem generally.
Okay.
The sweet spot seems to be clear, typed text, reasonably well-structured forms, scan books, things like that. But, for those really difficult, maybe old or poorly scanned documents, that's where you'd probably reach for the higher token modes like Gundam. Give the model the best possible visual shot.
Makes sense. Now let's address the elephant in the room, or maybe the philosophical debate. Compression. There's skepticism, right?
There is, and it's a fair point to raise.
The argument goes, a vision token, being this high-dimensional vector, can actually hold way more raw information, more bits, than a simple discrete text token, which is just an index.
Mm-hmm.
So is this really compression, or are we just shuffling the data density around?
Right. That's the core technical question.
Yeah.
And if you're just counting raw bits, the skeptics are correct. A dense vector holds more potential information than an integer ID.
So?
But the paper's claim, and I think this is crucial, is that this is about computational compression where it counts.
Yeah.
In the attention mechanism.
Okay, break that down. Why does that distinction matter? Even if the vision tokens are dense, doesn't encoding them cost something up front?
It does cost something to encode, yes. You pay that price once per document or page, but the massive savings come repeatedly every time the decoder needs to attend to the context. Because attention complexity scales, roughly, with the square of the number of tokens you're attending to. By drastically reducing the number of tokens, from 1,000 text tokens down to 100 vision tokens, for example, you flash that quadratic cost.
Fewer items in the attention matrix.
Exactly. It also means shorter paths for gradients during training, potentially better GPU cache usage, all sorts of computational benefits. The bottleneck for long context isn't usually the raw storage size of the information. It's the cost of computing attention over that information. DeepSeek attacks that bottleneck.
Okay, that reframes it significantly. We're not making the information smaller in bits necessarily, but we're making the computation needed to process it much, much cheaper.
Precisely. The computational savings are the real prize here, enabling practical scale.
Got it. So let's look ahead. The future of document AI. We've relied heavily on our retrieval augmented generation for dealing with large document sets. Does this optical context compression make RAG obsolete?
No, not at all. I think they're highly complementary.
Yeah.
RAG is fantastic for discovery, finding the right needle in a colossal haystack of, say, millions of documents. You ask a question, RAG finds the relevant snippets.
Right.
Optical compression shines after that. Or when you already have a specific document you need to understand deeply, it allows for whole document reasoning. The model can potentially hold an entire 500-page contract and its working memory, represented by these vision tokens, and analyze how Section 7 relates to Appendix B and Figure 3 all in one go.
So RAG for finding, optical compression for deep analysis of what you found.
And it's a great way to put it. You use RAG to pull the document, then DeepSeek OCR lets the LLM actually read and reason across the whole thing efficiently.
And this ties back beautifully to that memory decay idea for AI agents.
Absolutely. It suggests a new kind of memory hierarchy. Keep the very latest interactions as raw text for perfect recall, but as context gets older and maybe less immediately critical, roll it into these compressed image representations, maybe start at high res, then fade to lower res. It gives you that 10x or more effective capacity boost.
It's a very elegant system-level way to manage the trade-off between fidelity, cost, and how much context the model can handle. So for developers listening, people who actually want to use this, what's the practical takeaway? How does it fit into existing systems?
The nice thing seems to be that you can slot DeepSeek OCR relatively easily into existing pipelines. It acts as this highly efficient structure-aware reader at the front end. It gives you back not just text, but potentially clean Markdown, structured tables, even bounding box info if you need it, all while keeping the token count for the downstream LLM really lean. This could simplify the whole process and make the overall system cheaper to run.
Yeah, the potential to simplify the downstream tasks is huge. And the code, the weights, they're open source, available via Docker. So the next step is really for the community to grab it, test it, throw your worst documents at small mode, at Gundam mode, see how it handles them, measure the end-to-end cost savings in real-world scenarios.
Put it through its paces.
Exactly. Real-world pressure, thoughtful benchmarks, that's what's needed now.
Okay, so wrapping this up, two main things seem clear. One, DeepSeek OCR isn't just better OCR, it's fundamentally a context compression machine using images to fight token inflation.
Right.
And two, this could seriously change the cost equation for working with long context and LLMs, making whole document reasoning more feasible. I think that's spot on. It offers a really fascinating new path for scaling AI context. Maybe the future context window isn't just about brute forcing more memory or bigger models.
Yeah.
Maybe it's about being smarter by design. And maybe, just maybe, that intelligence starts by letting the model actually see the page before it reads it.
A different way of seeing leads to a different way of understanding. Something to definitely mull over next time you're faced with a giant PDF. Thanks for joining me for this deep dive.